Welcome to another dynamics video where we're going to be looking at kinetics or kinematics of particles. As you can see from our FE exam topics review, kinematics of particles is on our list of topics, so some of you might find this helpful in reviewing. So let's get back to the problem. So we have a car B is traveling a distance d ahead of car A. So let's see. So here we have car A, or excuse me, this is actually car B, is traveling d distance ahead of car A. So this is car A, we're going to put him at the origin, and so this distance is d. Both cars are traveling at 60 feet per second when car B suddenly decelerates at 15 feet per second squared. It takes car A 0.75 seconds to react and then decelerates at 15 feet per second squared. We want to determine the minimum distance between the two cars as to avoid a collision. So the first problem with this statement is we need to determine exactly what's going on with these two cars. Car A or B all of a sudden decelerates at 12 feet per second squared. In car A, it takes him 0.75 seconds to react, and then he decelerates at an even greater rate at 15 feet per second squared. So car B suddenly hits his brakes, so now it takes 0.75 seconds, so his velocity is even slower than it was before, and car B or A has to hit his brakes harder as to avoid car B. Lots of cars A's and B's. But let's see how these relate to in terms of equations. So from our kinematic equations, we are given that the displacement is equal to the initial displacement plus the initial velocity times the time, and it is added to 1/2 times the acceleration times t. I'm going to put this in capital T squared. That is A, acceleration. So if we want to do it in terms of B, his displacement, so the displacement of B is equal to the distance, because his initial displacement is d away from A. We want to add his initial velocity, which is 60 feet per second, times the time, or multiplied by the time, added to 1/2 multiplied by the acceleration multiplied by the time squared. So this time that we're using in this equation is the time that it takes for these two cars to get to the same distance. So that's why we are not putting 0.75 seconds in there, because we want to see at what time are these initial or velocities the same. And we can do that by the other kinematic equation, velocity equals the initial velocity plus the acceleration multiplied by time. So velocity equals 60 feet per second minus 12 feet per second squared times or multiplied by the time. And this is the velocity of B. So now we want to see what's going on with CarA. CarA, it takes them 0.75 seconds to react, but eventually when these two get close together, their velocities are going to be the same. So we have the velocity of A is equal to 60 feet per second minus 15 feet per second squared multiplied by t minus 0.75. We minus 0.75 because he is behind car B, so the time starts when car B hits his brakes, and so that's why car A is, his time is slower, because by the time their velocities equal each other, car A will have a shorter time than car B. So now we can put these velocities equal to each other. So we have 60 minus 12t is equal to 60 minus 15 plus, let's see, 15 times 0.75 gives us 11.25 minus 15t. So the 60s cancel out, and we're going to add the 15t to the other side, plus 15t. So we have 3t is equal to 11.25. Divided by 3, divided by 3, we have a time of 3.75 seconds. So the time of 3.75 seconds is the time from when car B hits his brakes that these two velocities will be zero. I mean, not zero, they will be equal to each other. So now the 3.75 is what we plug in to our displacement formulas up here. So let's plug it in and see what we get. So again, S equals S naught plus V naught multiplied by time plus 1/2 AT squared. And let's do it in terms of car B. Car B is the one that's ahead. So his initial velocity, or his initial displacement, is D plus 60 times 3.75, and we're going to add 1/2 minus 12, and then it's going to be 3.75 squared. So reducing all this again, the displacement due to car B is D plus 60 times 3.75, which is 225, minus 3.75 squared times 12 times 0.5 minus 84.375. So this is our displacement from car B. Now we want to do the same thing with A. So SA is equal to S naught plus V naught times time plus 1/2 AT squared. So we have SA is equal to, so his original displacement, so his time, or he takes 0.75 seconds to react. So from the origin, he goes 0.75 seconds. So 0.75 times his velocity times 60 gives us 45 feet. That means he travels 45 feet before he ever hits his brakes. So his original displacement is going to be 45 seconds. And this equation that we're going to be using is from the time that he hits his brakes. That's why his S naught, his original displacement, is 45. Because we're all equating it back to the origin. So we have 45 plus his initial velocity of 60 multiplied by t minus 0.75. Let me go ahead and write that in here just so we have t minus 0.75 plus 1/2 a t minus 0.75 squared. So we have plus 1/2 negative 15 times 3.75 minus 0.75 squared. Let me go ahead and write that in here for this t. We have 60 times 3.75 minus 0.75. So we have the displacement at A is equal to 45 plus 60 times 3, which is 180, plus 180 plus, so we have 3.75, so it's 3 squared times negative 15 times 0.5. So that gives us plus plus a negative 67.5. And that is the displacement due to A, car A. So now, when we go back here, when these two have the same velocity, they are going to be right behind each other. They're literally their distance between them is so small. That's what we mean by them avoiding a collision. And then, since this is A and this is B, A has a greater deceleration rate, so it's going to eventually go backwards relative to B, because it's going to slow down. It's first going to catch up to B, it's going to come real close, and then it's going to start pulling back. So from the origin, when we first calculated the time, these displacements are going to be the same. I mean, yeah, you're going to say, well, yeah, car B is a certain length long and has a certain length, and car A has a certain length, but we're only dealing with kinematics, meaning everything here is a particle, or we're going to treat everything as a particle. That's what makes this easy with kinematics. So we're going to say that the displacement of car B and car A is the same. So now we have 40. So now we can add all this stuff up. So we have 45 plus 180 minus 67.5 gives us SA equals 157.5, and SB is equal to D plus 225 minus 84.375, which is 140 plus 140.625. So now setting these equal to each other, we have 157.5 is equal to D plus 140.625, and D is equal to 16. What is it? 157.5 minus 140.625 equal to 16.875 feet. And that is the answer. That means the minimum distance that the two cars can be away from each other is 16.875 feet and not cause a collision. Now we can do it another way, and that is by using another kinematic equation, which is v squared is equal to initial velocity plus 2 times the acceleration times s, the change in displacement, s minus s naught. So once again, we want to find out what the two velocities are whenever they do equal each other. So we're going to have v is equal to v naught minus 12, or let's just write it in general real quick, plus, that is not a plus, plus acceleration multiplied by time. So v equals 60 feet per second minus 12 times 3.75 seconds. So we have negative 12 times 3.75 plus 60. So whenever these two velocities are equal, they're going to be going at a rate of 15 feet per second. So now this gets plugged into there. So we're going to first do it with car B. He's the one that's ahead. So what we have is 15 squared is equal to 60 squared plus 2 times negative 12 times his overall displacement minus D, his initial displacement. So we have 15 squared minus 60 squared gives us negative 3,375 divided by negative 24 is equal to S minus D. So divided by negative 24, so we have 140.625 plus D is equal to S. And now using this equation with CarB, it has the same velocity, so we're going to be using 15 squared is equal to its initial velocity plus 2 times negative 15 times s minus s naught. Remember, s naught was 45 because that was his displacement whenever the time started for him. Whenever he started hitting the brakes, he went 45 feet. Or let's see where, yeah, right here. So we have 45. So once again, we have 15 squared minus 60 squared gives us negative 3375 divided by negative 30 is equal to s minus, I guess I can drop the parentheses, x minus 45. So we have negative 3,375 divided by negative 30 plus 45. So we have s is equal to 157.5. So now this displacement and this displacement are equal. So once again, you just set them equal to each other. So we have 157.5 is equal to 140.625 plus d, and 16.875 is equal to d. 16.875 is equal to d. So we get the same answer using two different formulas. The hardest thing about this problem is just seeing that A and B, at what point these two are going to be equal to each other in terms of displacement and velocity. You just remember that B hits his brakes first, so he's going to be slowing down, which means A is going to be catching up to him, and then he eventually hits his brakes, but these two are going to get so close together right here. These two are going to get so close together, and then they're going to start backing away, and we call it zero. I mean, technically zero is them hitting, but I mean, you can, it's pretty much zero. It's so dang close to it that, yeah, I mean, it's not real world situations, so that's how we get away with it. But let's see, where did I put my answer? 16.875 and 16.875. So if you have any questions, feel free to leave a comment. I'll try to get back to it as soon as I possibly can. And if you have any suggestions for me working my next videos, please don't hesitate to contact me, and I'll do my best to get it worked out. Thank you.